and ASP.J implementation. So, ti potom prídeš alebo... Dobre. So what's one of the next duties that expects us is the test, and we actually talked about this, and we talked about moving it further ahead, but we finally agreed that it's fine for the test to be next time. So it means that now is the last possibility. So I hope you tried some code in ASP.J, and this is the last possibility to talk about ASP.J and theme.uml, theme doc before the test. Of course, you can send me a question, or you can post a question in our AIS forum, but it's probably best to talk in person. We can arrange additional consultations, but time is short, and you probably have other things to do. So I hope you will make use of the time here to discuss anything that might be unclear with ASP.J and theme, so that you can complete your test at an acceptable level. I mean, there's no any limit that you should reach in terms of the points, but it's probably not a very good idea to lose 10 points just like that. It's 10% of your grade. Okay. Any questions, anything before we begin with the lecture? So my idea is to first have a lecture, then the presentation, and then we can discuss everything else. Probably the presentation will come up, I don't know, after the break, but we'll see. Okay. It might not be a very long lecture, we'll see. Yes?
Just about the test, is it going to be in English or Slovak? I guess
in English, but you can respond in Slovak.
Okay.
If that's a problem for you, if you would not understand some question there, expect the test to be in the form that is that was as it was in last year. So you have an example, or a year before that. Of course, the problem will be different, but you will be asked to provide theme doc analysis, theme UML design, and ASP.J implementation with an application of one of those three aspect-oriented design patterns we talked about here. Okay, so we had already different ways of looking at aspect orientation, and in this lecture I'll try to present yet another way of looking at aspect orientation, which is based on components and composition, component and composite approach to aspect-oriented programming. First of all, when we talk about components, at least a common understanding of a component in object-oriented programming is that a component is a unit of modularization exceeding the size of a single class that may be connected with other such units in different contexts. It came out from the experience that a class is typically too small. Okay, it can be quite big, but if you make a class very big, then we lose perception of what is it about, what is its intent. So with respect to this, usually we need to pack together several classes in order to have a feeling of some complete part of an application that can be perceived as some kind of virtual. That notion is used for other purposes, but it's like some kind of virtual machine or something like that that can be then later maybe used in other contexts, and that's actually the main thing there. That it's not too much about the size as it is with the connections to other units of that nature. So we perceive something as a component if it is composable, connectable to other such units. And the main goal that we want to achieve by this is reuse, so that we can take program a component once and use it many times. I used slightly imprecise language there, connect, maybe there, might mean something else, or maybe some other notion might be more appropriate. Composed, which is a notion that we already encountered within other approaches or discussing aspect-oriented programming in general. So, what is the difference between being connected and composed? When you think of it. Do you feel some difference between those two notions?
Something's connected, it can exist independently.
Okay.
I mean, like when when the car is composed of something, you leave the car, like you lose everything that was in it.
If you last thing that you said?
Destroy the car,
yeah,
then you will lose everything that was in it. But if the car was somehow like connected some external system, like you destroy the car but the system still exists, and they were in the relationship of being connected.
Okay. Any other opinion?
I think the connection is more dependent. Composition is, I think, more lightweight.
You mean that composition is more lightweight?
Yes.
I would say otherwise. The composed objects are more integrated and are more difficult to detach from themselves.
If I try to draw a picture of it, if I put one component and another component like this, how would I connect them?
Yes, that's
Simply drawing an edge. That's of course that's a representation. Then in component diagrams, we usually have some in UML. I mean, a notion of ports. What is a port? Nobody knows, but essentially, there's it's intentionally actually made abstract for us to fill in the meaning of it with respect to different ways of implementing components. So, but if you draw some kind of square, there's something, some element, some additional element that provides means to connecting to other components, or some kind of interface or whatever. It might be another special class that plays this role, and so on between all those classes that implement a particular component. So, but anyway, there is some kind of connection, some kind of whole, something like that, and these two components are essentially quite independent and not overlapping. But if we make, for example, if you consider notion, of course we can give any meaning to any word virtually, and the meaning is different depending on the context. But if we think of composition and composing and so on, usually what comes to our mind quite quickly are music compositions. Music compositions are not just sets of elements that are independent. They're overlapping sounds, voices, everything that make the composition. And we may perceive these different voices, different instruments, the different tunes that they play as components. And then the composition is actually something that arises from two components or several components overlapping like this, rather than being composed like this. And this is something that is horrifying from this perspective of I want to have my system built out of components. I take one component and another component and wire them, and that's fine. But this is horrifying. This means that I need to mess with the internals of the components. And that's where aspect orientation comes in. Yeah? Wherever there is a mess, there are several if we would take that C1 is red, then maybe there are elements like this overlapping inside, several of them, and we must consider how to implement them, which comes first, which comes next, and so on. And that's these are our pieces of advice and or introductions or intertype declarations, actually, as they are called in aspect J, introducing further elements and so on. So this is a mess, of course, but aspect orientation can help. And exactly, people doing work with components mainly along these lines came to this idea more or less independently of that hype with aspect orientation, but since it became hype, so it became widely known and they recognized some things there, so they tried to align their component-based approaches with aspect orientation. So different approaches have appeared they are not very alive anymore, but I think they are worth mentioning. So this is actually basically what we are going to talk about. I don't know. I mean, I think this there's no sense to stick to these questions anymore, because we approach this in a little different way. But that's what I actually said, that pieces of advice in asymmetric aspect-oriented programming in aspect J can help us with this mess there. And we don't need to go directly to code with this. If we think of theme UML, those point cuts that are modeled there are provided in a language-independent way. So if you think of the design that is provided by theme UML, what is interesting there, it's not just what I said, that they are provided in a language-independent way, but that they are provided as being independent of specific join points, because we want still to have our components, to make our components as general as possible, to apply them in different contexts. So if I have an I don't know, insurance system, and then I have some banking system, and then I have some academic information system or whatever, I might make use of a certain component in different ways if it is general enough. And I still can compose it like this. And I compose it by using pointers. So if we recall theme UML and how the implementation of theme UML point cuts, which are its themes presented in a general way, maybe I should still have some time to show one example. This may be difficult to get to it. I want to show you just to recall how that theme, a general cross-cutting theme looks like in approach. So this is something we had before. This one, something like this. We don't need to have the most complicated or any complicated case. Just simple case with practically just one small adjustment made by this specified by this sequence diagram. So this theme actually, although it is called exclude alarms connected to special sensors, I might have called it in a more general way, because it is excluding a specified operation in an operation class. What is an operation class? I don't know, whatever comes to this thing. It is added there by composition with other themes, and the domain specific name came out of the analysis that we performed before. But the theme itself is quite more general. There's operation, there's a condition, and we come to these elements to mean something in terms of alarms only by composing this theme with the rest of the system, with applying this theme in the context of alarms. But we could also apply it in other contexts, and we may observe then that we have this general design, not cluttered with some details of the context. And when we take a look at implementation in aspect J, the most we can do is to say that we have some kind of point cut call operations that we will specify further in a derived aspect. Although we can also define this interface to play the role of the operation class, it's there just for the sake of having this parameter or argument sufficiently general, not bound to the specific context. And if we get back to compare this again to this theme, you see that there is a complete point cut there in that sequence diagram. And that's something that we can't achieve in aspect J. Okay, that for the sake of completeness, there's this derived aspect included there, but as we see, our point cut there is quite specific, and we need to involve the turn-off operation and so on. The most we can do is to include this operation class instead of a specific class. However, consider this code. This is not aspect J anymore, of course. It looks a little bit different, but still it's based on Java. I think that what's most confusing is what is a hook, and hook is of course for hanging. So we want to hang onto something, and this is actually our advice. So a hook is a special construct in this language that means practically advice, the same as advice in aspect J, or say maybe not directly a piece of advice which is here. It seems so, at least, but this is just a package for these special aspect-oriented constructs. So it's a little bit differently organized than aspect J. But looking at this first part here, well, if a hook is actually a special class within a class, then this looks like a constructor, and this constructor, since this is a special aspect class, is not actually a normal constructor. Rather, it's a way to express a point cut. And look at that point cut. The point cut is saying that we should capture some method called executions. This is quite similar to aspect J. What is the name of that method? It is not specified. So this is an identifier that stands for method names, but we do not specify any name pattern yet there. So this is a quite the general way to specify a point guard very close to what the theme approach offers us. And this is just whether this whole thing is applicable, and this is what we are going to do once we capture these method executions. But we need to bind particular method names to this, and we do this by when we instantiate this hook by providing something that is called a connector. So only in connector and in the theme approach, recall that you are creating connections between the themes, and via those connections actually you provide or bind parameters like this, the binding connector. Okay? So it's the same thing here. So it's quite close to what we have in theme approach. There is the name pattern is very general, of course, but we could have put here a particular method name. So this is to capture all method executions. So any name, there's a sum. Any name, in any package or with any return type and any arguments. It's a little different than aspect J, but the thing is that we bind to a particular specific method only in this connector and keep initial design, and we are capable of expressing the kind of the point guard within our code. This is actually no longer used object-oriented language. Actually, I don't think it was really used to implement any serious application like or that was used in practice. It's called Jasco. I don't even remember what I cannot even recall what this acronym exactly represents, but S is for aspects and Co is for components, J is for Java aspect components maybe, or something like that. So this is a this was an effort to come close to aspects or include aspects for making more composable components. And as you see, classes are once more used to make those bigger units that we consider to be components. So some kind of class nesting mechanism was used there, but for composition purposes they felt that they should go for aspect orientation. Of course, this was inspired by the aspect J approach, but at the time that the JASCO occurred, there was no theme approach. And the authors of the JASCO approach do not mention the theme approach as the inspiration for their approach. I don't think, again, that as similarly as the theme approach does not mention the ORM method by Trigger and Scalp. I don't think that this is intentional, that they stole the idea and they just didn't want to uncover the source. The thing is that they discovered the idea. And that's something quite strong, that different people come to the same idea independently. Another thing to think of software systems is by identifying the states they can or their parts can be in. That's an alternative way of thinking. We can think of how the system behaves and what happens and so on, and identify some sequences of the behavior, and that gives us actually a method called sequences or control flows. But as you know, UML includes also state diagrams or state machine diagrams, where we think of the system as transitioning from one state to another state. And the two things, the operations and functions, or functions of behavior, operations and states are connected, because a state is an ability to perform an operation. In some states, if you consider I don't know, an order in an e-shop system, an order cannot be dispatched just independently of the conditions that it is in. So if there's just an order that just has been created, it makes sense. It cannot be dispatched, delivered, then and so on. There is nothing there, and it is not confirmed. So we need our order to be confirmed, so that it can be dispatched. And being confirmed is some kind of to confirm an order means to call some kind of operation to confirm it, and to dispatch means to call some kind of operation to dispatch it. But we can also perceive this through states, and we can have these states represented as attributes, of course, but sometimes it's just a number of methods that or operations that have been applied before that made an entity become prepared for something else. So there is no physical notion of a state, of that state, so that, okay, you know, what we can read that attribute and say an order is in that state or not. Typically we have that capability, or we have such attributes, even for other purposes, for being able to display them in the user interface. But sometimes that's not the case. And that's something that I want you to think about. So an ability to perform an operation might be given by a sequence of operations without any kind of flag to rely upon. If that is the case, how can we know what state the entity is in?
To check the history.
We must check the history.
The
Yeah?
operation before.
We must check the history. Where is the history? It's gone away. Yeah? We must know that in advance, so we must follow the history. Yeah? So that's the goal. We must follow the history. And to follow something, to track something, to log something, well, that's something for aspects. And exactly, let's imagine this example, this very simple example. So we would like to log user activity between their logging in and logging out. Not too much to follow there, but something is there. So we want to follow this whole thing, user activity, whatever it is, and we start logging. We start logging when the user logs in, and after they log out, we stop logging. The logging in and logging out, that's not the same logging, okay? Monitor user activity between monitor, track, whatever. So log is meant by to make notes on what happens there, that first occurrence of this notion, and logging in and logging out is meant with respect to the activity of the user, of course. Okay, so if we consider this in an aspect-oriented sense, or not, maybe not yet, might note these activities for now as logging in is P1, user activity is in between, so it's P2, and the final thing is P3. So let's just see the idea. So in aspect-oriented terms, then those P2, P1, P2, P3 become actually point cuts, because we need to capture those. So user activity, we need to capture user activity, which may be quite variable, so different operations that are performed. So that would be kind of a you might expect quite a general point cut there. But we want to capture this only between the execution of the methods captured by these two points, that's P1 and P3. And P1 should capture logging in, and P3 should capture logging out. So in aspect J, we don't have actually a way to specify these terms, because this works. Okay, these 3 point cuts we can capture, but we cannot capture actually. We cannot actually express say that capture P2 in between P1 and P3 yet. There is a way to express this, of course, and this is actually quite a deterministic thing, but the system needs to keep track of what's happening to be implemented in such a way. So if we remain with Jasco, there's yet another thing interesting in this language, and this is practically an aspect-oriented programming based on a state machine. So, as in all state machines, we have some place to start, or must start somewhere. So we define where we start. We start by capturing P1 calls or executions. Actually, everything here is based on executions. I'm not sure whether just code works with calls or not. But that's not quite important at the moment. We specify what P1 is by this expression. So this looks like a normal, almost like a normal, yet general point cut, of course, because there's start method and log method and stop method, and we will actually bind them to the existing methods in our connector, which will come further, but that's something that we learned a moment before. So without these expressions there, following this not normal execute primitive point cut, these point cuts look quite like in aspect J, with the difference that we are using is proxies to represent methods rather than specifying their names. What is interesting is the second part that actually represents the transition or possible transitions. So when we are in this state P1, we can transition to P3 or P2. P3 means stop method, so that's the end. From P3 we can go again to P1, so it goes infinitely. We log in again. In state P2 we can go in P3 or again to P3 or to P2. So start method goes either to the end, so we log in and log out, or we log in and perform something as many times as we want, some user defined, some user activity there. We just this is the log method or user method, whatever user activity method, and that's it. And then we can say that before all this, we actually have our advice performed. And this is the code of this. This is just like in aspect J, just to show the drawing point. So if you have a look, if we want just to address P2 point cut, we can do this. Just to know that we can have a specific small other pieces of advice addressing specific point cuts that are defined there independently of their involvement in that state machine. So that's actually not very important, but we can have a look at what would happen if we apply this to some highly simplified system that involves some kind of start-stop method and some performance method. So our X method plays a role of the start method. Z method is the method that we actually I'm not sure actually, but this I can't tell because I don't have the connector. So I need to show you the connector. Maybe it's not important very much to see the code before. That we had before. So here we have the connector. So still it's nice to have this connector again. So we need to hang on to these start method, log method, stop method, which are actually introduced as formal parameters there. So start method, log method, stop method up there, and in that order we introduce X, Y, and Z. So this is login, this is user activity, and this is log out, and this is an additional method just to see what happens. So it is called, maybe our log out method calls another method, so it's normal to have further methods, not just these methods in the system. And if we apply this, advice, which actually just prints out our join point, would give us this output. So we are transitioning from x to y and z. So that's if we follow this, that's what happens. So in x we call y, so that it's this y method. That this y method calls z, and after this we go. Just a moment. We start by x, then we follow by y executes z, and we are out. Oh yes, there are two executions there. So these are the implementations of methods, and we execute this once and then again. I forgot that I had this included just to make it obvious that the thing will work again if we execute it again. So our start method is x, so we have this call there, and this is called again there. So that's why we have the same thing written out or printed twice. We also include, or there's also included what is implemented by the ZZZ method. Okay, so this is a way to there is a way, and it's possible to work with something which is called stateful point cuts, and consequently stateful aspects. Unfortunately, we don't have this functionality in aspect J. Okay. Maybe some things were confusing, or anything you would like to ask or comment on? This is just to demonstrate that if we start by z, we can also call z, which is log out, but probably would not make very much sense. But our aspect won't capture that, because there's no transition through to those states as specified before. We will get back again to the notion of components, and to the idea that components consist of several classes. And these classes need not be complete. So in composing those classes, maybe those red classes define some elements, maybe those blue classes define some other elements, some are overlapping. So we need to treat that separately. But anyway, we talk about something which we might call partial classes. In this drawing, it looks like, okay, we are composing them and so on, but how could we compose them in reality? How could we compose them in code? So there's another approach to this that enables us to compose those partial classes, which comes close or implements something that we call symmetric aspect-oriented programming. So what we had before was asymmetric aspect-oriented programming. So now we are going to see how some other non-aspect J approaches, or one of them implements symmetric aspect ratio programming. Consider this example. We might have some representation of well, an electric scheme where some components, electronic components, are connected via their pins through and by to each other by wires. There are some methods to work with this, which are presented there. And if we think of this, of those components that we have there, they are those electric components. So they're connected to somehow like this. I don't know, maybe different symbols that we would use there. I'm not using intentionally anything that would look like. Maybe they're connected actually. Some have several connectors. Some are transistors, some are resistors, and so on. These are not the corresponding symbols, of course. But anyway, our electric scheme or circuit, actually, electric circuit is practically a graph, and this is a graph that I just drawn. There are many useful algorithms to be performed upon graphs. So we might have a general component for dealing with graphs. That component consists of several classes, and these classes in this language are somewhat special because we would need them to be composable in a particular way. So these are not just plain Java classes, but they look for most of what they are like normal Java classes. So there are methods, there might be attributes there, but they are not there included now. So those called C classes or Caesar classes, like Caesar, and this language I'll reveal that it's called Caesar J, so it's based on Java and extends Java with those C classes. Can be packed in another C class like this, and then actually what we need to do in order to apply this component, which might be a bigger one, so bigger than represented there. So there's an edge, there's a node, there might be different things included there. Maybe some algorithms that can that enable us to efficiently work with graphs. In order to apply that interesting functionality to our graph, so electric circuit graph, we need to compose both of these, and the composition is done by extending this graph class and specifying how these graph class elements wrap the existing or domain-specific elements. In our example, there are electric circuit graphs. This is not that simple, of course, so you need to get on deeper into this composition, so it's not just enough to declare that an edge wraps a wire, which is quite logical. So our wires are actually edges, but we need to define how actually what does it mean? What does it mean to get start nodes, which is this method, in terms of the electric circuit, and that what being roped is called ropy, and we must get to its get start pin method and then get the owner of that method in order to return the node, which is actually the node is in terms of our electric circuit actually a component. So I don't want to bother you with the details of the syntax, but they needed to it's actually quite not very intuitive and not very attractive, but they needed to do this in order to make things composable this way. So this is a way to compose if you have some, to say so, legacy code in Java, and you develop your aspect-oriented components. This is a way to go there. So this does not look like having some piece of advice affecting something. This is rather something like this, overlapping, or this is the case. Maybe more like that. This one graph component gets over completely this electric circuit component. And there's another. This is just further code related to this example, which is not quite important at the moment. But this roping and Caesar J is what we've talked about. There's another way of dealing with component compositions in Caesar J. If we forget about legacy code in Java, so we don't have legacy code in Java, we're developing everything in Caesar J, then we can exploit full capabilities of those C classes. So those C classes are then composable in maybe I would say in terms, or not just this, I would say that the composability is an extension of what we know as inheritance and overriding. So just as you can override methods in Java, in C classes you can override nested C classes. If you have a Java class and some nested classes there, and another you define an extension of that class by the extension relationship and put some other classes of the same name, you're not going to override those classes. There's no such mechanism in Java, but in Caesar J there is such mechanism. And let's consider our cuckoo's egg example, and maybe it's I would make it funny. I would use code to develop my former PhD student, which I adapted a little bit. Actually, I don't mainly the identifier names. I'm still not fully satisfied with them. So we might even discuss the difficulties with naming correctly C classes. But consider this simple C class, which depicts our that includes just another C class that represents an egg. So we are going to talk about cuckoo putting her egg or its egg into somebody else's nest. So for this we need to have a complete egg situation, to say so. So the original egg situation actually extends this basic egg situation, which considers only an egg class, and there we have a nest where the egg should be placed. We are not actually very interested in representing correctly this that an egg is in a nest, but we are just going to inform that the nest contains the appropriate egg, and the appropriate egg is or what egg does the nest contain, and what egg actually it is revealed by the egg itself. So we create a new egg, and it's being being say so executed. So what it does by being executed is that it reports what kind of egg it is, and then we just have some kind of the starting method or main method, which starts everything by creating the nest. Okay. So this is the original egg situation, and the report, if we run this code, the report will be, of course, that the nest contains the original egg. But we can maybe don't need this part. What we need, or what happens in the cuckoo's egg situation, is that that egg is no longer the original egg, but a cuckoo's egg. So we define another C class that actually has another kind of egg. It's still named egg, it's within this cuckoo's egg situation class, so there's no name clash. And then we have an overall cuckoo's egg situation, which actually represents a composition. So this is a symbol, this and sign, ampersand sign, means a composition of classes. So cuckoo's egg situation is composed with the original egg situation, which is this, and this is cuckoo's egg situation. So this is composed with this. So this egg class, which is actually these classes are virtual classes, practically. This mechanism is called virtual classes. This egg class will override this egg class there. So we have, if we have this main method to run everything. So if we start this original egg situation, we will get, of course, the output that the nest contains the original egg, and when we start this overall cuckoo's egg situation, we will get this. Something to observe is that this egg situation, we need to define this egg situation first, and we need to derive, to say that, to declare practically that, that we will be dealing with interchangeability of this C-class egg by deriving the both original egg situation and cuckoo's egg situation from the same base C-class. So that's kind of a limitation of the approach. And only then we can override the whole class in the composition that actually is achieved formally by creating a new C class which extends the mentioned composition. So maybe it wouldn't be necessary to use this extends, or something else might be used there, but they probably wanted to stick as much to Java as they could. So this is practically the composition that is being defined there. So I was in trouble a little bit. I used some other names. There my PhD student used completely different names, and it was quite confusing. What is an egg situation, original egg situation, and then cuckoo's egg situation, and then again this overall cuckoo's egg situation. I didn't know how to name it properly, so I used such names. So the egg situation that contains only this egg class is actually just a partial egg situation. So this original egg situation is the whole egg situation. So I hope that the names are not that confusing. So you recall the implementation, I hope, of the cuckoo's egg in aspect J? No? Look at it. You have an example, even in those, might be another example in one of those test examples. In aspect J it's implemented by a piece of device. Yeah, so you have something that captures a pointer that captures a constructor, and you capture that constructor, and you hold it with your around device, and then decide whether to run it or to run some other constructor or some other class and provide that object instead. Okay. Yeah. But that's a piece of advice, so that's asymmetric. And this is a composition of classes where you achieved the same behavior practically. Questions, notes, remarks, complaints? If not, I'm going to finish here. So what we saw is that aspect-oriented modularization can be applied to components. So we can perceive components in an aspect-oriented way, and we saw three approaches in two different aspect-oriented languages, which are no longer used, or they have not had that kind of life that aspect-J has had and is having still. They were not sufficiently popularized with the community. They were mostly developed as research prototypes, although there were attempts to make them community accessible and accepted. There are links connected to this or introduced at the website of this course regarding this lecture, that you can check those websites of these languages yourself, so that they still exist, and maybe they could be even actually try it out, because there are compilers that are available. So you need to use an older version of a Java compiler with them, or an older version of Eclipse and so on. But anyway, what is important for us is to observe what happens there, and maybe observe this in other languages that are not considered to be aspect-oriented. So we might spot some similar things, maybe to some extent, in some other languages. Those three ways that we discussed there are named here. So the way that the aspects are connected can be decoupled from specific joint points, which were implemented by hooks and connectors in JavaScript language. We also saw that we can define point cuts based on state configurations there. And the last thing is that how components can be connected at the level, or on the level of partial classes, which they consist of. Which actually, there are two sub-approaches. So there are roping and virtual classes, both in CSRJ. One is more related to the legacy code that we might have in Java, and you want to rope by aspects. And the other is if you are developing new code in this CSRJ language. Think of this in terms of what we discussed regarding the theme approach, and the ability of the theme approach to represent symmetric, aspect-oriented design, and something that was known, and think of this in terms of something that was known longer before in that all-around approach. So that's all for today's lecture. We will have one more lecture, not next time, but after that, and there will be no more lecture from my side. I'm eager to hear your presentations, and we will refer back to what we had in lectures in the discussions, and I hope that what we discussed so far, what I presented to you so far in these lectures, will help us have and maintain a common vocabulary and understand each other better. There are no questions. It seems so. So that's all. Thank you for your attention. We might have a break now and then continue, and then finish probably earlier. We might have then consultations, individual consultations regarding the project, if you wish.